Okay, so this is the second part that I mentioned earlier. So truth is here we have to change pace. But before we do so, I have to make some very basic observation. So be it clear that I don't want to patronize anybody, because these observations are very basic, but I have presented this material other times, anytime that I didn't start with these observations, within 10 minutes was a complete paper, and after 10 more minutes it had become a complete circus. So in order to avoid this, I will take the chance and make these observations. So this thing doesn't work anymore.
You press with the mouse.
If you press on the screen, usually with the mouse.
With the this one is that's it. Okay.
Yeah.
Okay. So statistics and probability. What's statistics? Statistics is a collection of procedures, tests, estimations, regressions, etc., which essentially tell you how to use the available information to assess certain aspects of the phenomenon under consideration. Ultimately, via the concept of loss and error, this procedure stems from a set of rules that allow the statistician to evaluate real value functions on a space. The other object is probability. This is usually when the paper starts. Probability theory is what? It's by definition the study of a family of probability spaces, of the most among these spaces, and of the associated operators from the real value functions on one space to the real value functions in another space. So concretely, probability theory is this. You have a given probability space S sigma Q, and you have a collection of subspaces S beta Q restricted to beta. So here beta varies among all the possible subspaces of sigma, and this is the restriction of Q that is defined on sigma to this subspace. Okay, the operators, what are the operators I was referring to before? These are the conditional expectations operators. So once you have that B1 is a subadjunct of B2, you associate the measurable functions on B2 to B2 to the conditional expectation that is a measurable function. Okay, so these are the two objects of interest here. How do they come together? They come together because Savage, this is 1954, gave the foundations of Bayesian statistics in this book. And how did he do that? He didn't say it. What he does, he maps statistics into probability. Okay, and this is how he found all the statistics. So how does this go? Okay, essentially we've already seen any axiomatic system in decision theory is a way of evaluating functions on a space. If we take that space as the sample space, this is implicitly, or at least when you make this evaluation, depending on the information that is available, this is going to produce some sort of a statistical problem. Probability theory is something that does provide you with rules for evaluating measurable functions on a space, in particular the sample spaces, on the basis of the information that is available. What does probability theory tell you? Tells you, you want to evaluate this function. This is your information. Take the conditional expectation of these functions. Expect the information. Okay, notice that if you, in the case of no information, is the case where conditional expectation is equal to the expectation. Okay? And so as I said, if you regard, this is something that solves the problem. Okay, Savage, how does he solve the problem of found in statistics? By mapping the problem, these rules into these rules. Okay, so statistics into probability. Mechanically, how do you, by doing this? Okay, before you have seen axiomatics in decision theory, just intuitively what you have to do is you have to complete this axiomatics by explicitly introducing information. So one way to do this is not the only way, even the first way, but you can assume. So what you do, you assume a family of preferences parameterized by events in the sample space. Okay, and you interpret these preferences as the set of rules that the statistician is there to follow if he knows that event E obtains, if this information is generated by the fact that he knows that E obtains. And then you would have to link these preferences to one another. So since now you have a certain familiarity with the system of axioms that I mentioned before, one way to achieve this axiomatics, these Bayesian statistics, is to impose the first 6 axioms of expected utility, but on each class of conditional references. Then this is the one that links these preferences together. Here, this notation means this would be the function that is equal to f on event E and to G to the complement of event E. And this is an assumption that is a history, has generated lots of debate. It's called the dynamic consistency. This is another pretty famous axiom that's called consequentialism that essentially states that the conditional preference must depend on the event only. Okay? Okay, so once you have, what happens once you have done this thing? So just use what we have seen before. So to begin with, remember that sigma algebra sigma is generated objective, the one that makes all the functions actually. What is the information available to the statistician? This is determined by the events that the statistician is in a position to observe, the data that can be gathered and observed. And so, since we assume that the statistician knows how to the logical operations and induction, it's the sub-sigma algebra generated events that can be observed. Now, what does that type of axiomatization do? You have seen already that the first 6 axioms applied to each conditional preference give you a measure space. Okay? E sub-algebra, sub-sigma algebra generated by E and measures on E. Then the 2 other axioms, 7, 8, and 8, do what? They imply, if you work them out, that all these ones have to be the conditionals computed from one of your space, QS, and that you have to evaluate functions by means of their conditional expectations on the sub-algebra. Okay, so this is exactly the rules of probability theory. Okay, so you see that essentially that system does what? Says the rules that you have to follow are precise the rules of probability. So this is how you map the problem of determining those procedures into probability. Observation. Notice that from the viewpoint of probability theory, to evaluate a function by means of the conditional expectation is the best evaluation we can give on the basis of information. Of course, this means something only when you have specified the notion of best that you're using, and this is the model of construction. Probability theory, the notion of best is the one expressed via the norm. So the conditional expectation of a function on sub-algebra beta is the closest function in the distance, or as you know, the projection with respect to this norm on subspace of beta measurable functions. Okay, so the bottom line is that the job that those 6 axioms that we saw in the first part about expected utility do what? Map these rules that the statistician has to follow into probability. What comes out is, as you know, the Bayesian Bayesian statistics, And so Bayesian statistics, being descended from this map, is founded on the ideas statistician is a probability measure on the sample space, and that the random variable is evaluated by means of its best L2 approximation, those functions that are measured. Okay, so such this kind of definition. Okay, so if you want, if you look at this, because from here on, things become complex. Okay? So why am I saying this? Because, you know, honestly, this is a point that in a way surprisingly, when many professionals have difficulty on, honestly, I don't understand why, but if there is something that you feel that is unclear, you become spent well if you actually clarify something. Okay, so okay, this just in case the police is going to come after me. I am not using Savage original axiomatic. I said it this morning. I'm using Ascom now because I think it's more transparent. Conceptually, the type of axiomatic that you use is immaterial as long as you map in the first place. Skip some details, not even that much, really. If you look at Savage book, Savage introduces only the axiom, the unconditional axioms, and then assumes Bayes rule. Okay, but you can prove that Bayes rule is equivalent to axiom 7 and 8 given the first 6. So this is why I put it that way. A very nice paper that actually uses the Savage axiomatization to show that it's equivalent and Bayes rule is equivalent to this two is this one down the middle of 2000. Okay, so Savage map builds Bayesian statistics by mapping statistics into probability. Let's make some obvious observations. To begin with, you remember at the end of the previous part, I spoke about the problems encountered by Bayesian theories to deal with dynamics. And I made the point, of course, you know, there is a problem there, because if you do not understand what kind of statistics is associated with these models, you cannot seriously solve the dynamics. In fact, you can, the problem is not even that you cannot solve it. You cannot even check if you have done something meaningful or not. Why? So evidently people have done something. It's not that nobody's done anything. What have they done? They have essentially made non-Bayesian system parameterized by the event, by information, and then they are added two more axioms, like in Savage. Sometimes they added exactly the same axioms, which should tell you that there is some basic examples in this case. Why? What do I mean? Even check if this works on me. Because Savage did this. Okay, the mapping here is the axioms of Savage, that system that I've written before. This is the same. If I change the mapping, evidently here I should find something else and not find the same thing. This should grant me that this is obvious. No? But if you don't know what it is that is on the other side after your axioms, what are you going to check? There is nothing to check. So evidently, intuitively, I should find something that is some sort of an alternative. But if I don't know what is this alternative, without descriptions associated with alternative theory, how do I calculate the equivalent conditional expectation? I need to remember, and this is why I think that all these attempts have failed. In particular, this one. You know that under Savage axioms, 7 and 8 is equivalent to Bayes rule. Now, essentially, you're putting some sort of base rule. You don't even know where to put it.
So this doesn't work now, even if we refine the axioms, like add some additional things.
The point is not the axiom. The point is that you have to understand what's on the other side. Savage knew what's on the other side. Savage was determined in finding the other side. This is why generative measure, so you have a generative measure space of reference, and via Bayes rule conditional expectations. You just think that once you have this, you have all Bayesian statistics, tests or regressions and stuff like that. Here, the problem is that we first have to understand, once you change the axioms, what you're going to find on the other side. Okay? So, essentially, this is what we're going to be doing. And how are we going to do this? So first of all, we're going to try to get a sense of what we find on the other side. And then we will use this sense to develop essentially some sort of general framework, which will tell us that here, dependent system of axioms can be associated with a certain class of alternative probabilities theories, and we'll see how is this going. So, if I mean, so this I have to say. I want to skip it, but okay. So, what are we going to show first? We're going to show that many Neo-Bayesian models, so special cases of the models that we have seen in the first part, produces some alternative theories of probability that are pretty much almost the same as classical probability. We will see that essentially they just differ in the notion of approximation of one uses. But what's the upshot, and in particular something that might be interesting or useful to you, is that once we will see this, we will have automatically a statistical paradigm which stems from the mapping. And besides solving at once evidently the problem of dynamic extensions, but we will see that the statistical paradigms are different from the classical one. But they're better suited to a bunch of problems that have emerged, like robustness, outliers, insufficient data, etc. All things that these days, one way or another, big deals. And in fact, we will see that lots of techniques that are already in place can be regarded as the equivalent of classical techniques in this alternative probability. So in particular, this will be the case for robust statistics, robust regression, penalty functions, etc. You will see them popping out pretty rapidly. If a teacher example, make the effort to associate these things that probably you have seen, you will make the link pretty easily. Okay, after the evidence, as I said, I'll go construct a general framework, essentially identifying a class of generalized probability theories and the statistics that stem from this. I will show you, hopefully I'll have time, this will be this, how you can build mechanically in this framework new theories, automatically new theories of probabilities and associated statistics. And as an example, I'll show you that one that pops up pretty naturally is one that can as a pretty sound statistical meaning. I hope to have time to get here because normally, one thing that I learned in school is that typically when you start with general stuff, it's a sound practice to recover the existing stuff. Make sure at least that you're not in it delirium. And evidently, since Bayesian statistics has to be a special case, one exercise here is to rederive Bayesian statistics. What's interesting is that something new comes out. something new about Bayes theorem comes up, which honestly surprised myself because it's still an English, so it's pretty surprising. You'll see. I have presented this to a bunch of Bayesian statisticians, pretty famous. The amount of screaming is quite fun. Okay, there are several implications that come from this in terms of updating value information and any consistency. So I won't have time to go through this for sure. In any case, most of this material I will retrieve it from my webpage. Part of it is on a paper that I published recently in Mathematics of Operations Research, and some of it is in a couple of working papers that are available to CCP identified. Okay, so this is something that we know already. That it's the model as functions. Okay, we have already spoken about the measurable structure on S. So as a consequence, it's clear these functions will be a subset of all the bounded sigma measurable functions on S. And from here on, I will assume that the functions that one has to evaluate are all the bounded measurable functions on some sigma measurable functions in the sample space. We said what is the information available to the statistician is determined by the events that the statistician in a position to observe. And so it is represented by the sub-sigma algebra generated by these events. What does this mean? Means that once this is your information, what are the functions that you understand? Okay, the functions that you understand are the functions that are measurable with respect to your information. And so we will, I will denote them by like this, 0 beta, and all the functions that are beta measurable. This is all substantial, there is nothing technical about this. What does that mean? If I cannot tell you the rule, if I have never seen this rule, I cannot estimate how many chairs are in this room, how many tables are in this room. Okay, as far as I am concerned, on the basis of the information, this room is a point. There is nothing that I can meaningfully say about this room. Okay, if I can pick this, okay, maybe I see something and I can make a guess that maybe I don't know, 5 tables, 6 tables, etc. So this is what psychology is. Okay, information, you use it and tells you what type of functions you can approximate. So for instance, if I can see 2 tables, I can guess that there are somewhere between 4 and 8 tables. Okay, so if a function has to be defined on tables, I can approximate it with functions that can take between 4 and 8 values. Okay, and so this is the same thing that you do with data. Okay, so this is this object play a role here. Okay, just as a reference, for ease of reference, I will distinguish between the static case, by which I mean the case in which the statistician is in no position to observe any events. I cannot see the room at all. In this case, the algebra, no information, empty set, the algebra generated by the empty set is this one. The measurable functions on an algebra like this are only the constant, evidently. So these are the only functions that I understand. And instead, in dynamic cases, I have some observations available to me. And so I will denote by this the sigma algebra generated by these events. Okay, so once again, now let's give a little more formal look to the basic Bayesian paradigm, and then we will start building the evidence toward non-Bayesian statistics. So here, basic for the moment is not important, but basic means the paradigm after the predictive is being calculated. I'll get back to the general one later. Okay, so what's the point? Just now, regard this as a translation of what we have said so far. The axioms of Savage map statistically to probability. What is probability? You have reference measure space, omega sigma q, and all the theories prescription are derived from this class of optimization problem. Given f, a sigma measurable function, determine its best approximation in the class of functions that are measurable with respect to your information. Best means what? The one at the shortest distance according to the other. These words. Okay? So this is probability. Imagine that you know that the projection theorem gives a unique solution to these minimization problems when the algebra is trivial. What is the solution of this problem? Remember, the trivial algebra, you have to look into the constants. This is the only thing that you understand. The best approximation is the constant function that takes this value at any point. What is this value? The expectation of f. And so this gives you precisely the expected utility function, the function that associates f to its expectation. What happens in the dynamic case? Okay, the case as you certainly know is this one where this is a partition of S of non-zero probability event. What is the best approximation? You know that it's this simple function here. This simple function is the conditional expectation of f on the subalgebra generated by these events. Okay, and so this produces the conditional expected utility function. F is associated to this evaluation with an AI. Okay, it's familiar? Okay. So see, now we have restated, we have said Savage, the rules of Savage are obtained from this. So the axioms are in a way a transcription in terms of references of this procedure. Okay, so notice there is something remarkable about this theory, that it's its owners. So both the evaluation criterion and the appearing rules, so the way in which you process information, are derived from the same principle, that you do the best you can, given the available information. Best, you solve a minimization problem. Okay, which is this one. And notice also practically how good this is. You know, certainly better than me, how important it is to have a simulation or other description and derive the solution to the optimization problem. It's the entire theory that comes from this class. Okay, so as it is at the moment where before we said this thing, okay, so now you change the axioms on the right. Yeah, we must find something else. Fine. So 125. At the moment, we cannot. One thing that at least I thought was a good strategy to begin with was to say, okay, so why don't we change this thing just a bit? And then we ask ourselves, is there a system of non-Bayesian axioms that takes to this theory, change theory that we have created? One observation that honestly I thought was pretty obvious is, okay, given the structure of the theory, what is the object that is a little bit conceptual, a little bit arbitrary? Is the notion of approximation. We have to know. Conceptually, it's nothing special, but we have to know with respect to other known linear divergence functions. And therefore, I thought a good strategy would be that of starting to change this notion of approximation and see what one finds. Obviously, I had already in mind something that I already know, because probably I have to say this first. Notice that in this way, conceptually, the theory is the same. It's just the notion of approximation that changes. Okay? Okay, there is something that was familiar to me, and I'm almost certain that is familiar to you as well. An obvious change there would be to replace the L2 norm with the L1 norm. Okay? Since I mentioned that they've done stuff in data analysis, etc., remember that classical regressions come from the L2 norm, least squares and stuff like that. One of the motivations, for instance, to run the regressions with the L1 norm instead of the L2 norm is the robustness for class. And to know average is sensitive to outliers. What does the L1 norm mean? The L1 norm is medians. Medians are not sensitive to outliers. In fact, it's been long known that the solution to the same problem as before, once you replace the L2 norm with the L1 norm, is a median. Any median is the solution to that problem. Now, the next observation is what? Okay, medians are not unique, so you have to add some selection criteria, but no matter what selection criteria of the median you add, this is a narrative that has long been known, the median functional is a Chauvet. And so this tells you why. Okay, so if I change the L2 norm into the L1 norm, I find an object that I know how to get from the axiom an object like this, because this is a Chauvet. In particular, the capacity is unique, and this given by this. If you solve the dynamic problem with the L1 norm and the L2 norm, so you get the conditional evaluation function that is again Chauvet integral, and so implicitly you get the updating rule that is associated to this process that is this one. So the bottom line is once you replace the L2 norm and the L1 norm, on the right, you find something that looks a lot like standard probability theory. You have just changed the notion of approximation. Which axioms tell you that you there? You know the answer for this model. There is a system of class of Chauvet expected utility model with some additional axioms that imply that the capacity is this form, that the rule is this, that take you exactly. Okay? So you have now a Neo-Bayesian decision theoretical that produce. Now you know what this model produces a new theory of probability that is very much like the classical one, except for the notion of approximation, and that is new statistics that stem from this part. Okay. If this is understood, I will mention the other two examples, but I would like to go fast. So if it's not understood, I'll just go. So, okay, so again, the idea was, what do we find to the, now go back. So this is procedures that we want to fix. There is a, you can interpret all of this by saying there is a system of axioms that belongs to the Chauvet expected utility class that brings you into this set of procedures. Evaluations that are Chauvet integral, conditionals evaluations that are Chauvet integral, this is the updating. Okay? Okay, so now this means what? That if you have to build a regression, instead of using averages, you're going to be using Chauvet averages. Testing is they're going to be done with these capacities and not with those probabilities that use Bayesian statistics. You can mimic exactly the development of Bayesian statistics just starting with these objects instead of probabilities. Okay? Okay, now this is another exercise. Instead of the L2 norm, you can replace the L2 norm with the sup norm. And again, what you're going to have here is, you were talking about sup and image before. Yeah. So what you have here is another Chauvet expected utility model. The capacity here is different. This is going to be the updating rule that is associated with this model. By solving again the utilization problem, so now you can repeat the same thing that I said before. This is another thermal probability and therefore another statistics, and this is associated to another Chauvet expected utility.
Just a big stupid question, but these are kind of the. So you take the L2 norms, the L1 norms, the L infinite norm. But what if you have a general L norm, like ST or L4 or whatever? have an idea or an intuition of what would happen, even with the updated rule that, how it will change.
Okay, so
because at the beginning, when you presented like the
okay, no, I understand the question. The thing is this: one thing that will emerge from this, it was something that some of us in this context, I don't suspect, is that. So unfortunately, this will take us.
okay.
But this is the thing. In the attempts that have been made before, we were dealing with capacities, and so many tools for capacities. And we had the sense that some of us had the sense that this wasn't a good thing to do. That this idea that you could use like a base theory, the incapacity, didn't make very much sense. And here you find an answer. Each model is to be updated via the solution of this minimization. So you can have a model with the same capacity, but that is not this model, that produces another. So this is not surprising by any means, because this essentially mathematical is what you would have expected, and the properties associated with linearity are extremely strong. There is a lot more leeway when you're outside linearity, and this is what we expect. Pretty much. So one thing, another thing here is to go beyond noise. And at that point, if you start thinking like this, maybe why just noise? Why not divergence functions? As you know, divergence functions are usually defined as some sort of generalized distances along probability measures. Here, I'm talking about divergence functions between random variables or random variables. I introduced in the paper I mentioned before a class of this divergence function building on the notion of Amarante in the divergences of numbers. The details are not important. The divergence function that I use here is this one. What's probably a bit important is that this mapping is strictly increasing from positive numbers. So once you reconsider, here again, the exercise is take the base of parameter, replace the two norms with the divergence function, what do you get? Okay, so the reason for doing this is that solution with the quasi-arithmetic means, which I spoke before, and the conditional version of this. Once again, you get another paradigm, same fullness as the Bayesian model, same logic, just different from the notion of approximation, and an entirely new statistics. This is something that we understand because these things have been around since Montréal. So in a way, it was a way of saying, okay, these models can really generate something that the statistics has been done and we didn't know why, and now in terms of foundations. One final observation about this. This is one of the models that I mentioned before by statistics. So by statistics, we said before that they take this form. This would be the penalty function. I had mentioned that in by statistics, often this takes the form of a divergence function between probabilities and the reference. This proposition shows that this object is quasi-arithmetic mean, like one of the previous slides, only in two occasions, when phi is the identity and when phi is the negative exponential. When phi is the identity, then this is expected. But when phi is the negative exponential, the solution, the equation here, is the relative. So you get what I had mentioned this morning as the most popular model in robust statistics. And so now you have an axiomatic foundation. The axioms that we know, that we had the solution that this alternative probability theory where you use divergences rather than no, than the two no, for this model that, as I mentioned, is most popular. Okay, so in sum, We have changed the notion of approximation associated with the basic Bayesian paradigm. In this way, we have obtained three paradigms that have the same logical foundations. Bayesian paradigm, a whole in the sense that all the paradigms of description are derived from a unique class, a unique optimality principle, and hence from a unique class of optimization problems. And for each of these paradigms, on the basis of this work, we are able to provide axiomatic foundations in Neo-Bayesian statistics. Okay? So this is the evidence that what I was proposing holds water, because now this is shown. Now comes the next general theory. Ask me a question if you really want to ask a question now, because the general theory is not, it's considerably more difficult than this. Can't think about this. So again, the idea was what is to the right of the other? Yeah. And to the right of the other, we started saying, okay, let's suppose that it's this, and we find some axioms that would work to procedures in this. And in this way, okay, so practically, I mean, this stuff about medians, vastness about lives, can derive already from this model. Statistics that has all these features. The equivalent of the regressions of least squares done for the L1 norm, aside from the fact that computational is a little more difficult, but you can derive it entirely from this. This is stuff that actually you find already, because I mean, this is the subnormal evidence is a robustness problem, in the sense that we consider all the different subfunctions, and there are lots of methods in terms of regressions, in terms of testing, on this stuff. Same you can say about quasi-arithmetic means, because one of the reasons why they've been around forever is essentially that via this generalization of the very mean, you could encode lots of desiderata like robustness. Okay, so now 15 minutes. 15? Yeah, that's all. Okay, then we will not do anything. Okay, so general theory goes like this. I take as a basic concept that of statistical model. That is a set of probabilities. Why do I do that? Because as we mentioned before, we know that any Neo-Bayesian system, think of a 1A5, is going to produce a statistical model. In fact, the assertion is even more general. There are weaker system of axioms than a 1A5, but still are going to produce a statistic. This represents the uncertainty perceived by the statistician. You're uncertain about these probabilistic descriptions. Once you start in this way, there are typically two problems that pop up. One is that saying that you're uncertain about certain probabilistic description of the world means that there are certain relations among random variables on the sample space that are associated with the statistical methods. The first essentially bit of a technical, it's not really a technical problem, but the problem that you face is that these relations cannot be encoded in an algebra of functions unless you have only one probability. Essentially, why? Because basically, suppose that you have a partition of S into A and B. You have a function that is strictly positive on A, F is strictly positive on A, at 0 on B. G is the opposite. Which one dominates which? According to one probability, the probability is supported by A, F dominates G, maybe G dominates F. So these type of relations cannot be expressed by means of an algebra of functions. The second problem is the statistician receives information about the sample space, so observes realizations, sample space, data, sample space, how does he use this information to update the statistics? Okay. For a quick comparison, in Bayesian theory, you do have a statistical model. The theory produces a prior over the statistical model. You take this prior to average among probabilities in the statistical model. This average probability is called predictive, is the one that you use to make your assessment. You receive information about tests what you do. Your Bayesian used by Bayes theory. And in this way, you update the statistical model. There is another way of going, but let's see. Okay, this is how the problem is solved in there. Okay, so the theory that I built out as you go. So if one first shows that the statistical model is canonically associated to a certain algebra of operators. Then you show that this algebra of operators encodes all this relation among random variables, the ones that you cannot express by means of an algebra of functions. You can express by means of this algebra of operators. Then you show that there is a canonical mapping from the object that is your object of interest, the functions of sample space, into this algebra of operators. And you show, it's a pretty routine thing, to show that this canonical mapping is an algebra of homomorphism. And this is the key property of the order instructions. Why? Because it permits you to, so this answers the first problem. I said, okay, so all these relations, you have to represent them. There is this algebra of operators that does the job. How do we update? By, you show this, so once you show this, you have shown essentially that you can translate any information about the sample space in terms of information for this algebra of operators. This is intuitively what the implication of the fact that this mapping is an algebra of operators. And then what do you do to this algebra of operators? You do exactly the same thing that we were doing in the examples over the functions. You fix norms, divergence functions, etc. And this algebra of operators, each norm of divergence functions produces an alternative. And then pretty much what happens is the same that we saw in the examples. So since I have to touch, see, might be a bit of a confident, but essentially this is pictorial. This is shows you how the theory is. So you're the statistician. Everything comes down to being able to evaluate these functions. Okay, this is the functions of the sample space. Once you're informed, you get some information, you say the sub-algebra, sigma algebra generated by A. How do you do that? Remember, in the example, you have to project or solve this minimization problem on the algebra of functions that you understand. You want information that you expect. Point is that you have to state the problem here. You cannot state it here because there are many measure spaces. In the examples, we could state it here because there was one measure space of variances. Okay, the Q, not in the examples. But here there are lots of PQs, etc. So you have to state it somewhere else. You have to state it. So now this algebra of homomorphism property tells you what? This is in fact an algebra of functions. Saying that phi is an algebra of homomorphism means that the image of this algebra is a subalgebra. So you can read this algebra here. But it also means that the image of any subalgebra here is a subalgebra of this algebra of operators. Not only says that think of the solutions of the organizations as generalized projections. Whatever projection that you take here, it's carried into a projection that you take here. Okay, so basically, you can read your problem in here, and reading your problem in here, you're going to respect your returns. Once you have that, then the game is somehow simple. Here, you play the same game where you played in the examples. Okay? Pick norms or divergence functions and solve a minimization problem. So now, an F is associated to a certain operator here. These are the operators that you understand how to evaluate. take the best approximation of the operator corresponding to F, you evaluate it, and you evaluate F this way.
Okay. So how do you get this commutative graph?
This, the commutativity here is just the fact that the mapping is algebra homomorphism. Yes. So essentially tells you the image of any subalgebra is self-algebra. Given this, whatever projection of algebra to subalgebra happens on one side, happens on the other side. Okay, this is the statement of the minimization problem in the algebra. We're not going to repeat this, but basically the theory would have, whatever theory built in this way, would have the same features as we have seen in the example. All the descriptions of the theory, all the statistics, the alternative probability theory, the statistics that come from it, all come from the solution of the same class of minimization problems. And this theory is different from one another only for the notion of approximation that you use as expressed by a known divergence functions. Okay, this is okay, I'll speak first. These ones. So essentially, this is something to say whatever it is that we're doing this morning. Now we will define it in this way. So the algebra operator says lots of norms, and particularly you can define any of the LP norms. When you define the L1, you're filling in all, like in the example before, you get these double intervals like this, where this is a capacity. And so we know that these are special cases of the axioms identified. So now we have identified the alternative probability theories and some of the alternative probability theories and the alternative statistics that correspond to axioms 1 and 1 to 5. This is a very special case. In correspondence of the similar divergence functions just adapted to the norm that I defined before, we get this functional like this, that is exactly the smooth model that I had mentioned this morning. When function phi is the power function, x to the p, the limits give you the maximum max. So as you can see, we do have the alternative probability, the alternative statistics that are associated to these well-known models. As an example, here, one node that appears in this construction that is pretty natural because we were talking about operators, is the operator node. This is a new node with respect to what we have done this morning. The model that emerges is this one that can be described in words. It's pretty interesting, actually, from a statistical viewpoint. So it goes like this. So you have this statistical model. You have a probability on it. You compute the average, like in the Bayesian model. You compute the prediction. Now, the next step that happens in correspondence of this operator node is that you robustify by extending all the probabilities to all probabilities that are absolutely continuous with respect to this average. Then for each of these probability, you calculate first the expectation and then the standard deviation. And then you determine the worst approximation error and you evaluate each function by means of the expectation corresponding to its worst approximation. So you can see it's a little bit of the flavor of min-max, but instead of taking the lowest expectation, you take the expectation that is associated to the highest standard deviation, which from an informational viewpoint makes sense because this is the one that exposes you to the highest, to the biggest error in terms of the information that you have.
And variability. Variability also.
Yes, and so it's a model that statistically makes a lot of sense. Honestly, I have no clue of this thing. I just calculated it because it was, first of all, it was not difficult to calculate it with respect to the operator no. There are lots of things that here you have to solve to have explicit things. There are lots of things that I was not able to solve. Essentially, why? Because basically there is another way to calculate. Instead of going to operator, you stick with functions, but you change the notion of multiplications. And if you change the notion of multiplications, and then you have to change the notion of exponentiation, and I wasn't capable. I don't probably not even that few, but I wasn't capable of making calculations with these different multiplications.
We have 1 minute.
Okay, 1 minute. Okay, then I will say this because I think that this is interesting and worth saying. So as I said, was a good practice to derive Bayesian theory. How do you get Bayesian theory? When you fix the L2 norm on the algebra of operators, you get Bayesian theory. The solution is what it has to be, it's this double integral, and this is a measure, and therefore you pass to the barycenter, the average measure, and the double integral collapses to this thing that is the same as Q in the basic Bayesian paradigm. This is the Q, the average measure. So what's interesting here, at least according to me, evidently here you do the same thing. Once you get information, how do you solve the problem again, and you get implicitly the updated. Okay, so now what is the update? The updated rule is what it has to be. So you update the statistical model with Bayes. Okay. What's interesting here is that Bayes theorem does not appear as an update. Bayes theorem appears in the solution of the minimization problem. Okay, so it's the solution for the L2 norm. And what's more, now in Bayesian statistics, one thing that forever was that you have the statistical. I give information on example space. You update the statistical model by using Bayes theorem, you recalculate the predictive involved. Another thing that you can do, you calculate the predictive in the outside. I tell you information about sample space, you can simply calculate the condition of the predictive. And you go on forgetting the statistical models. It wasn't only that these two procedures gave the same result. Okay, this rederelation of Bayesian shows not only that Bayesian theorem is the optimal updated rule for the L2 norm, but also that this is the unique rule that makes these two procedures commute. So either you re-update the statistical model and you calculate the predictive, or you just forget the statistical model and just update the predictive. So this is when it's based on all the Bayesian statisticians when we are in like maniacs. And when I like maniacs, because essentially their statement was based in Bayesian statistics is Kolmogorov plus Bayes. And he said essentially this shows you that it is that with Bayesian statistics is just the solution, best approximation problem when you see that algebra of operators. And so in a way, since that solution is Kolmogorov, Bayes theorem is Kolmogorov as well. So the whole thing is just Kolmogorov, which ex post makes sense, because if the idea of statistics is mapped into probability theory by the axiom, you should have not found anything else. And it shows that you do not find anything else. Okay? And at the same time, in a way, strengthen all the other things, because you say, okay, so see that in the other things, when it's no longer the L2 norm, you still would have a complete theory. There's nothing else that has to be added to the presentation. As I said, for me, there are, okay, just in 1 or 2 sentences, okay, aside from these implications here, evidently there is a lot that at least in my opinion, could and should be done in terms of actually deriving these statistics, these methods of interpreting new old methods in the slides like we have seen here, but also having new theories and new methods like we have seen in the example of the operator model. one of the reasons why I wanted to present this work, despite the fact that I understand that it's not the easiest thing to present, is that there are lots of stuff that I've not been able to do, lots of stuff that I like to do, more or less what I'm trying to tell you that I'm sort of fishing for co-authors, but I hope that I'm interested. Thank you.
Maybe one last round of the question. I don't know if anyone wants something, but okay, I have just I think this is, I mean, for me it was impressive. This Bayesian theory pattern, because it seems that you kind of clean everything. Like thanks to this correspondence, you managed to clean everything, looking at the probability space, right? Correct. I don't know if I get it correctly.
Yes, okay, I'm saying if honestly, when I went for this, I was really just trying to check that I was doing this. After I found the result, I realized that had I not found the result, it would have been a serious problem for my entire work, because essentially I would have said, no, there is something outside. Yes. Probability that is necessary for Bayesian statistics. So, and automatically would have applied it to all the other constructions that I made. So this exposed when I understood really what I was doing, I was very happy that I found this result. Ex ante again. Now I don't know because I wasn't a savage for either it's a stronghold of Bayesian statisticians. They're all descendants of some cousin, Definetti, etc. And so all those stories that you don't know. So the idea is this guy was writing something called Foundations of Bayesian Statistics, and this foundations is a system of axioms. So I think that the guy was very intelligent. So in a way, everything has to be done by those axioms, including the Bayesian. So since it was clear to Savage that he was mapping the work of the theory, exactly how he put it, in a way, exposed, yes, okay, because Savage was very smart. Fortunately, it turned out to be smart, because otherwise they would have wasted a lot of time.
And the last question, concerning like axioms, so from the probability system to the axiom of.
So this is something that actually I have discussed a bit. I don't remember if I discussed it in the published paper or in some working papers. So maybe I didn't discuss it late, but there is a gap in what I can answer you. So I can say one of the advantages of this construction being built on the notion of statistical model, we know at a very basic level that pretty much any system of axioms we're going to be using is going to produce a set of probabilities. If you're interested in how do we know this, because if you remember this morning at some point I said, okay, look, these axioms at the end of the day have to be stimulated, that you make an order with certain functions, and that this order has to have some regularity. Whatever rules we think of, this is at the end of the day, this is what's good. So it's a basic mathematical fact by what do I mean by basic mathematical fact? That if you take a space of functions and essentially you give it some instruction in the Banach space by duality, okay? This thing of that I've said on orderings translates into the existence of a certain subset of the dual statistics. Okay, so the reason for me was that, okay, so whatever axiomatic work you're going to do, it's going to produce a statistic. And so I provided the theory whereby the axiomatic work is going to go there. But now there is a little bit, some murky stuff, or some stuff that's not clear. Now, L2 norm. L2 norm is the linearity of the projection. So essentially, we know how to axiomatize it. The other norms, then I don't know what you have to do to axiomatize it, but to provide a full axiom system, essentially now you have to axiomatizing the other norm, the other notions of approximation. This is very good work, because I mean, this is going to tell you really what your theory is telling about. Because now you understand that the idea of inference in Bayesian statistics that is translated into Bayesian approximation is really the projection theory. What are the real intuitive ideas associated here? Robustness for outliers, robust optimization, blah, blah, blah. Okay, this is all work that has to be done. People that work on axiomatic foundations now should make an effort to understand what are these notions. And notice that in each great model, should expect there will be lots of different models. Already here, we have two more completely different models that belong to the Schleck-expected class. So the axiomatic work there, essentially, I would say, okay, yeah, I have shown you what you have to now do. I am not super interested in axioms, but I understand that was easy when the answers from these examples are easy because the answers were already known. Essentially, the object, one way or another, is already appeared. There is some stuff that it's probably reachable more easily. There is some robust statistics done by the 90s by Kadar and Lassen.
Yeah. Thank you very much again.
Okay. Thank you.